Hello and welcome. We have today an interesting Leetcode question, very hard problem, but one that if you have gone over previous concepts, it shouldn't be too crazy. So this is a graph question, and it was previously asked by Amazon. I guess other companies probably have asked it. Who knows? And the question is called find critical and pseudo-critical edges in a minimum spanning tree. So for those who don't know what a minimum spanning tree, the question does define it. And if you do not know what a minimum spanning tree is, then you probably can't solve this question. Um, Also, if you do not know what the union find method is, you can now solve this question. At least not reasonably. I don't know how else you would solve it. And also, if you don't know about Kruskal's method, Kruskal's algorithm, you probably can solve this problem. But in fact, if you do not know what Kruskal's is, I can like briefly explain that. With the union find, you should definitely like have done that research before you look at this video any further. Um, so without much, let's get right into what the question is asking of us. So it says given a weighted undirected graph connected with n vertices numbered from 0 to n minus 1, right? So it's zero based, and an array of edges where we have the source edge, essentially the source node, right, which is a and then b, right? It goes to b, and then the weight, the distance it takes, and then this represents a bidirectional and weighted edge between node a and b, right? So you can go to from node a to b and b to a, basically. That's what I'm trying to say by bidirectional. Now, a minimum spanning tree is a subset of a graph's edges that connects all the vertices without cycles and with the minimum possible edge weight. Find all the critical and pseudo-critical edges in the given graph's minimum spanning tree. An MST edge whose deletion from the graph would cause the MST's weight to increase is a critical edge. On the other hand, a pseudo-critical edge is that which can appear in one MSTs but not all. Note that you can return the indices of the edges in every under. Now, I really like this question because it's like they are really telling you what to do, right? So, maybe you've never made an MSc, but if you have, then you've used the Kruskal's method, right? And you can use Kruskal or prims to form an MST. But Kruskal's, we use the union find method. So in that method, it's basically union find is basically you're going to connect multiple nodes, right, based on the relationship given by the graph, and once nodes are connected, we can use our unified method to find, right? So there's a union, and then there's a find where we can find the parent. So let's see, I connected 1 to 2, right? Initially, in my parent array, we'll have each node distinctly pointing to itself. I see this pointing to itself. If I connect 1 and 2, right, I have to choose one parent, and I will choose whoever rank is greatest. Or you can do it also randomly, but in our coding, we're going to do it with the one whose rank is greater. So the one whose rank is greater is the one who we will make the parent. So let's see, one's rank is greater than 2, and rank just means size, right? Like the number of elements that are connected to it, basically to that current parent, right? If that is greater than 2, then I'll make one the parent. And with Kruskal's algorithm, what we'll do is that we will sort the edges based on the weights, right? Like from 0 to 4, we know it's the fourth edge, right? This 4, and the 3 says what it is having a weight of what 3, right? It's I and weight here. Let me explain this, but basically that is what it's saying. So with Kruskal's algorithm, we'll be able to form a minimum span tree because we will basically sort our edges based on their weight, right? With the minimum weights first in ascending order, and then we will pick the ones with the least weights, and then use our union find to join them. And eventually, we'll have something like this, right? Which is a minimum spanning tree. There are multiple minimum spanning trees. And the question essentially just tells you what a critical edge is, right? It's the edge whose deletion will increase the critical edge, or the one whose the pseudo one is the one where we remove the edge, and there's the basically the minimum spanning tree's cost or the cost of creating that tree remains the same. So basically, question already tells you what you're gonna do, and it's going to be brute force. But there are so many steps with this. This is why it becomes a hard problem, and also there are so many prerequisites, right? So without much ado, right? It labels let's just go through the example, right? If you've labeled you have 0 connecting to 1, right? You can see 0 connecting to 1, 0 connecting to 1 here, right? This occurs every time. And also this edge also occurs in all MSC. So this is a critical one as the question is previously defined, right? But some of these edges, like this one, for example, and this one, for example, they do not need to be there. So if it does not need to be there, because it's not occurring in all of them, then it's a pseudo, right? So one thing we will do in our solution is to first create our minimum spanning tree, the smallest we have, and keep the cost, right? And then we'll go through our edges and try and remove them. When we remove an edge, right, is the cost going up? Like we'll try and skip that edge. We'll make sure that in our minimum spanning tree or in our new find this thing, structure that we make, right, we do not include that edge. Now when we do not include that edge, right, is it going to be having a higher score? If it does have a higher score, right, then we return that what it's a critical edge. Like there's no other way we can do our minimum spanning tree without having that edge included, right? But if and also actually if we are unable to create a minimum spanning tree with that edge not being added, then we also know that's what a critical edge. But if we if we remove it and we are still able to form a minimal spanning tree, and the cost is still the same, then it just shows us that it's a pseudo. So it's a pseudo. So without much further ado, let me just write the steps of what we want to do, right? Because with union find there is a lot more coding, especially this is Java, so it's not as quick. So we want to create a union find class, right? And then we want to create our build MST class also. And then we first get the main cost, or the main cost is what's the cost of making the minimum spanning tree. And then from there we want to check for each edge and see if it's critical or not, right? So that's what we want to do. So first, instead of just having this function, I'll just keep this function empty because we know we use the union find method. So we want to do the union find class. So I'll do class union find, and then in the class we'll have an int list or for parents, right? Appearance, and then I also need the rank, right? The rank is like the size. You brush up on union find if you don't know understand what this is. Right? And then the number of components in our union find. So basically, actually, at the moment, we are decreasing the number of components. So if a number of components is equal to 1, right, then we know that we've touched all the edges and we've connected them and made them just one. We don't want distinct components left. So now we want to so basically we want to call our union find method, give it structure. So when it's called, we need an n, right? And then basically happens. We set to the rank and the parent, right? And actually components is initially going to be set to n, and then we loop through. Basically, loop from k is equal to 0 and k to up to k is equal to n. And once we are doing that, we are setting each element to be its parent, right? So parent of itself, and then we are setting everyone to initially have a rank of 1. And then I want an int method to do the find parent, right? So give it a variable find I, and then we'll have this condition, right? So while the I is not the same as the parent at I, you want to do a parent, you want to do a path compression and then set it. So parent and then parent. Right, this is path compression. Path compression, and then we see I is equal to parent I. So this is how you find an element. Sorry, a parent, with the union find method. And then I also want boolean, but this is for the union. And basically, I give it int I and int j. We want to connect two things. And we say we want parent I to be that we find the parent of I, and then parent j basically what we are finding the parent of j. Let me scroll down. So let's go. Okay, so now if the parent I, right? Sorry, if parent I is already equal to parent j, then they are already connected. So we want to return false, right? They are already connected. Already connected. If not, then I want to use the ranks, right? So the rank of parent I, excuse me. So if the rank of parent I is greater than the rank of parent j, then we want to use it. So then we'll see that then for parent j, right? So parent of parent j, want to set it to parent I, and then we'll increase the rank of parent I by the number of elements which were initially connected to parent j. It will be easy for me to just go and copy and paste my find, because it's basically a template that you consistently use. But for those who do not know or haven't previously seen it, I think it will be helpful if someone codes it out sometimes. Right now, you do the opposite for what's parent j, right? So the rank of parent j, basically. Then we add a not parent I. That's a parent I to it. I hope we did not make any mistakes. Right, so if we do make this new connection, I want to decrease our count of our components, basically, right? And then we'll return false when we make a connection. So that should help. And then the last thing we want to do is to return the components. Basically, so I'll use this when we're checking if we're able to actually make our MST. So basically, we want to return our components. That should be it. With a union find. So the next thing is make our build MST function. And actually, before we do that, right, I want to leave a shell of it so that we know where the build MST function will be within our find critical. So basically, our build MST, that's how we're going to build MST. We already have a find method here. So we want to just have the stuff that we'll use. Right? We want to keep what the critical nodes. So keep the criticals. It's on the edges that were critical, and then we also want to keep what's the pseudo one? I call it pseudos. You see, there are new array lists. And then our results array is a list of lists, basically, right? And now we want to have a map of our nodes, right? Because the question is basically each node, each element that has been given us, in our edges, right, is corresponding to an edge number, right? So what we want to do is to give it its corresponding edge number. So I want to store that with an edge, and then the integer that corresponds to it, I want to store that in the map. So having a hash map, and then we want to fill it, right? So we'll be filling our map with the corresponding edge values, right? So we'll say we're going to through each edge in edges, right? And then we'll see that our map, and we put in the edge, and then we want to be increasing its account. So let me call it val and declare it outside. So val or index, right? Wherever you want to go. So initially, in the first edge, we'll give val of 0, and then we increase going from there. So it will have everything sorted out, and then we can use that later on. So now, what we are interested in is what? As now using the MST. Now, first we want to get the main cost, right? So basically, the main cost is going to be the build MST, and in our MST we need the edges, and then we need what we need. We'll need the number of nodes. We need the one to skip and the one to keep. Before that, we want to implement Kruskal, right? So for Kruskal, I'm going back to edit it. So build MST using Kruskal's algorithm, right? Now, if you're using Kruskal's algorithm, then you want to, as I previously said, you want to sort the edges by the least weight, right? So before we even do our main cost and get to that, what we want to do is to sort the edges by the weight. I'm going to say array.sort, and we're sorting edges, and then if you take two edges called A and B, right, we're going to sort based on what the edge, and edge is the second. So the weight, and the weight is the, I think, the third element in the edges. Right, so basically sorted in ascending order, right? So sorting by weight in ascending order. So then once we've sorted it, then we can use that and build our MST, right? So let's go ahead and build the MST. So it's going to give us an end. We're going to build an MST, and I want to call. So basically, we need the edges, right? And we need the end, and then we need the integer array of who to skip, and then the integer array for who to keep. Now, to build an MST, you need what the union find. And as I previously said, we're using Kruskal, so we want to define a union find. I'll just call it union. Actually, UF will define that. UF union find, and we're giving it n edges. Yeah, right, and node. So it should be fine. Now, after building that, we also want to return the cost, right? So the cost of building the MST. MST is basically what we're going to return, right? Now, for our initial MST, we are not going to have to think in terms of what we want to skip and what we want to keep, right? But with this one, we do want to allow the functionality of our build MST to be able to do so. So what we want to say first is that something that we have to keep, right? Then for that one, we have to mandatorily have it in our union find, right? So for that one, I say for the keep mandatory elements, right? I'm going to add it to union find. So for that one, we'll say now if our keep is not equal to null, right? Then we have elements that we want. So I want to list it as a keep 0 as our I, and our J for keep 1. But we don't even need to list them out like this. I want to say that a union UF of the you want to unite what I and J basically. Right? We are definitely uniting them. So once we unite them, for sure, we want to increase the cost by the weight of what this union, right? And that will be what keep 2. See, that's the weight. So if we are adding mandatorily, right, then like you said something that we have to add, then we're going to do that. And then after that, we want to add all those elements that later on. And also, if we are adding, you do not want to add elements that we've told ourselves that are going to skip, right? So we see that basically we want to make sure that whatever we are using, right, is not the same as skip. Right? So we'll say very easy, right, to say if our edge is not equal to skip. So now if you're not the same, right, then what we want to do is to say that we have a boolean, and I'll call it unite. Right? I will call it unite and say union find union, and then basically I want to say okay, you're just not having to declare them out, but just say edge 0 and edge 1, right? The two nodes that are being connected. Right, so basically, we want to use this unite function to see if we've previously if we previously connected them. So every fresh connection, right? We want to increase the cost. So say the unite is only going to be true if this is the first time we are unite, and we are basically adding them. So see if unite, right, then what we want to do is increase the cost. So increase the cost by the edge weight. So it's edge 2, right? And then basically if our UL, if the components, right, if the number of components, if it's equal to 1, right, then we've been able to we have built MST, right? We finished making our MST. So that if so, we want to return the cost. it's fine, it's cool. Right, but if not, we want to return -1 to show we have not made the MST. So basically, based on, and we're going to do that later, right? But basically, our union find method is going to be employed because we're using Kruskal, right? And we've already sorted the edges by the weight. So we use UF cos 0, and then if we have to keep it, right, we forcefully add that to the union find. But if not, then we only increase the cost for the elements that we are now newly adding, right? So that's why we have this unite function. And if our number of components goes to 1, right, it means we've connected every single edge, so we return the cost. If not, I want to have something that will tell me that, hey, you have not been able to build the minimum spanning tree, right? So basically, we now here, going back to the main formula, right? We've done the first part, we've done the second part, and we've done the third part, actually, right? Where we get the main cost, right? Which is the cost of the spanning tree. And now what we want to do is do the fourth part, which is what? For each edge, we're going to check, right? We're going to check if we remove it, right? As the question says, if we remove it, then the main cost will go up, right? The cost we'll get will go up. Right, so the minimum spanning tree actually, so an MST edge whose deletion from the graph would cause the MST weight to increase. It's called a Kruskal edge, right? So if it goes up, Kruskal edge, if it stays the same, right, it's a pseudo edge. So basically, we want to look through all the edges, right? So we say for edge and edges. So for edge and edges, what we want to do is first get the index, right? So the index of the edge. So we say map get edge, right? Map comes in handy here. And now with that, we also want to get what's the cost without adding the edge, right? So basically, when we want to skip that edge, we'll say build MST, capital edges, and then we give it n, and then we give its edge as what we want to skip. So now with the other one, and then basically now for the other one, and then cost with basically. So if you are building the MST, so edges and the skip will stay null, and then we are including the edge, right? We are including the edge here. So this is nice. So now basically we just want to do what the question told us, right? So if the cost without is greater than the main cost, then what we have is what we have the Kruskal edge. But also without that Kruskal edge, it could happen that we can't build the minimum spanning tree, right? So that's why I have that if the cost without also is equal to -1, right? Then we have a critical edge, right? So if you have the critical edge, all I want to do is to say critical. I think I call it criticals, never mind. Criticals, we add the index, right? So the corresponding index for the edge, right? So if, for example, I try with 0 and the edge between 0 and 1 here, which is the 0th edge, right? The I. Then we just add that to criticals. And else if the cost without is equal to the main cost, then we know that like, even when we shun or we shun the edge, right, we still get the main cost, right? We still get a minimum spanning tree, so it has to be what is pseudo. So pseudos dot add minutes. That should be it. So basically just brute force. I'm going to do that, and I'll say now result or add. We want to add our criticals, right, to our results, and then we'll say results dot add also. We want to add as pseudos basically. So and then we want to return our results. Return results, and I'll try my best to get. I'll link, like I'll make a post so that you can link to the solutions. So it's easier for you guys. Okay, cool. So have essentially a few functions. Let's see if okay, they stack up. There are a few bugs. I think we can't find symbol main cost. So it means I had a small c here. Okay, so main cost and here also, right? Should fix that. Oh no, what is happening? The internet is so slow. Ooh. But while we read, right, just basically you go. So I think finally loading. And definitely there are a few bugs. This is my solution basically here. And I'll link that in the comments. But basically, I think there are a few issues with my code. For the first part, we want to use the cost width, right? So the cost width, that element, if it doesn't change, then it's still the same as the main cost, right? And this part has executed when we check the cost without, and it wasn't critical. Then if the cost is still the same, it's a pseudo, so we add to pseudo. So it's supposed to be cost with, no cost without. And also another error here where we want to return true when we just connect them. If they're already connected, we want to return false, right? Because this will go a long way in our unite. I think it had like a here, right? This boolean. So if this boolean is true, then we add to the cost edge. So those two changes. Let me have the code running. and then let's submit. We successfully like passed. Very good solution. What is the runtime? I think that's a good question to ask. So we have we sort here, right? Um in our function, and also we get the main cost here, right? So something will be n again, right? The number of edges we have, or the number of edges is n, right? And then the main cost, the main cost. Let's look at the function. What it does basically, we perform the union find method, right? And then the union find method is alpha actually. So I would say that we have a runtime of n log n plus n times alpha, right? So for each edge, we're gonna create, even though we're creating two like MSTs, right? Using the union find, because of how the union find methodology works with the path compression, will be fine, right? So basically that is it. Like for each edge, you're going to simulate adding I'm going to simulate adding, skipping an edge and stuff like that. So it's going to be what, n times n, right? So for one edge, we're going to do go through all the edges again. So it's going to be n times n squared times alpha, right? Which is the time it takes to get the union find. Because of the path compression, we have path compression down here. So you should take a look at the link in the description. If you like the video, please do leave a like. Thank you guys for being here. I'll see you on the next one.